Hi everyone, welcome back. This is our last lecture on basic objects and counting techniques. Here we're going to focus a little bit more on counting in graphs. The main idea is whenever we're interested in a counting problem, we have to decide what do we consider to be the same object and what do we consider to be different objects. So for example, when we were considering counting permutations or strings, order mattered. But when we were interested in counting combinations, order didn't matter. So in that case, we would have considered like the string ABC as different from the string ACB. But as a collection, the collection ABC is the same as the collection ACB. So in combinations, we didn't care about order. In strings, we did care about order. And so that's what this first example is really about here. It's what should we consider the same? What should we consider different when we're looking at counting problems in graphs? So just as a first example, which of the following graphs are the same? And I put same in quotes because I just want to get a feel for what maybe we should consider the same versus different. So have a quick look at these three graphs and just what is your gut feeling? What graphs should we consider to be the same versus which ones should we consider to be different? Now, of course, it depends on what we mean by the same. So if we meant, and I'll put a little question mark here, if we meant by same, we mean equal. Well, as graphs, these are equal if the components that make up the graph are equal. And so what is that? Well, we have a vertex set and an edge set. So for two graphs to be equal, they'd have to have the same V and the same E. So the same vertex set and the same edge set. That's what it would mean for two graphs to be equal. Do we want the same in this context to really mean equal? If we did, then unfortunately the second and the third graph would not be the same, because if you look closely, there are vertex labels there. The middle graph has vertex labels 1, 2, 3, 4, whereas the one on the right has vertex labels A, B, C, and D. Their vertex sets are different, therefore they wouldn't be equal. But they do have the same shape. So maybe we should just loosen up the idea of what we mean by the same. Do we mean equal? No, this is too strong of a condition to have. What should we mean then? Well, we'll just mean same shape or same structure. And that means we are just going to ignore vertex labels. So we will ignore vertex labels. And so we've already actually dealt with these kinds of questions before when we talked about listing all of the trees which were unlabeled and had a certain number of vertices. So what are all the unlabeled trees? Draw them all out. In that case, we are only interested in shape, not the vertex labeling itself. So that's what we're going to mean by same in this case. We mean same shape. So then coming back to these three graphs, we'll call this one G, this one H, and this one I. Which ones should we consider to be the same? Which ones are different? In this context, we're going to use same to mean same shape. So which ones have the same shape? Well, the first thing to note is that G is a cycle of length 4. And H and I are not. H and I are not. They're not cycles of length 4. So G has a different shape than H and I. So G has different shape from both H and I. So we wouldn't consider G to be the same as H or I. But what about H and I? Well, both H and I are triangles. So that's just another way of saying a cycle of length 3. So they're both triangles with one more edge. So maybe I'll say it with another edge attached. So they have the same shape. They basically both look like a triangle and then an edge attached. I'm just going to draw it like this for a nice symmetric picture. So we've got a triangle and an edge attached. So that's what they both look like. They both look like this. So they have the same shape. So H and I have the same shape. Now, same shape in mathematics, or same structure, whenever we've got some objects with a certain structure attached to them, and we say, well, I've got these two types of those objects, and their structure is the same, we call them isomorphic. And so in this case, we would say H and I, two different graphs, having the same structure as each other, are isomorphic. So to be a little bit more technical, what we mean by isomorphism is if G and H are these two graphs, given by vertex set V1, E1 for G and V2, E2 for H, then G is isomorphic to H, or has the same structure, if we can find a bijection F between the vertex set of G and the vertex set of H. Remember, a bijection, Macm 101, this is a function that's one-to-one and onto, or injective and surjective. Those were other ways to say one-to-one and onto, and if you had both those properties, you were bijective. So this bijection has to satisfy the additional properties that if you had an edge, UV, in the graph G, then the corresponding vertices, f of u and f of v, must form an edge in H. And similarly, if f of u and f of v formed an edge in H, then the corresponding vertices u and v form an edge in G. The function itself is called the isomorphism, so f is called the isomorphism, and we say that G is isomorphic to H. So let's look at an example. So we've got this graph G. Maybe it's got labels 1, 2, 3, and 4, and it's got edges that look like this. So there's our graph G. And we've got another graph H, and our graph H, maybe it has vertex A, vertex B, vertex C, and vertex D, and its edges look like this. And we want to know, are G and H isomorphic? Well, they both are triangles with an extra edge attached to them, so they have the same shape. So based on the fact that we're trying to build this idea of two graphs are isomorphic if they have the same shape, then our gut should be telling us, yes, they are isomorphic. But in order to show two graphs are isomorphic, we need to appeal to the definition and find that function f, which does what we want. So what is our function f? Well, f is going to be a function from the vertices of G to the vertices of H. So in other words, from the set 1, 2, 3, 4 to the set A, B, C, D. And so what we'll have to do is we'll have to define it. So I have to say what f of 1 is, what f of 2 is, what f of 3 is, and what f of 4 is. And I have to fill in those spots in such a way that two vertices are connected by an edge in G if the corresponding vertices are connected by an edge in H. So the first thing I'm going to look at is that vertex 4 in G. It's of degree 1, and there's only one vertex in H of degree 1. So 4 should map to A. And because 4 connects to 3, and 4 is being associated with A, and A connects to B, then that means 3 should get mapped to B. So we've got these mappings here where I'm sort of taking this 4 and I'm saying associate it with that vertex there. And therefore 3 is going to get associated with this vertex there. And then we've got the remaining two vertices, 1 and 2. They just form that other part of the triangle, and so they can get mapped to C and D in either way. So I could say 1 goes to C, 2 goes to D, and I have the property that for any edge in one of the graphs, the corresponding vertices make an edge in the other graph. So for example, if I look at 1, 3, under the mapping, 1 goes to C, 3 goes to B, and that corresponds to this CB edge. Or if I had this edge over here, BD, since B is the image of 3 and D is the image of 2, 2, 3 has to be the corresponding edge over here, and there it is. So this map, F, is an isomorphism. So F is an isomorphism. And we say then that G and H are isomorphic. Now, isomorphic, it quite literally translates to equal structure or equal form, or same structure, same form. So iso meaning the same or equal, and morphic meaning shape or form or structure. And so this quite is literally the translation of they have equal structure. So these two graphs have equal structure. They are isomorphic. This next example asks us to draw all non-isomorphic graphs with 3 vertices and all non-isomorphic graphs with 4 vertices. So by non-isomorphic graphs, it means we're only interested in the shape or structure. Before, we actually did similar problems to this. Non-isomorphic, we just mean basically unlabeled. And we've done that before. We've drawn all unlabeled trees with a certain property. And that's really all this question is asking. So we're using the more common terminology, the more technical terminology of isomorphism to just ask previous questions that we've already asked before. But we're phrasing it using this new terminology. So let's draw all non-isomorphic graphs on 3 vertices. So 3 vertices. Let's see, what are they going to look like? Well, I could have 3 vertices and no edges at all. So I'll use 0 edges. And there's one example. What else could I do? Well, I could look at a 3-vertex graph that uses 1 edge. And now, if I'm only going to use 1 edge, I'll just put an edge in there, anywhere. There it is. Do I need to look at the other 2 possible ways to fill in an edge? And the idea is, well, I could have this 3-vertex graph, and I could have used this edge. Well, this graph and this graph are isomorphic. Since we are interested in just unlabeled graphs or non-isomorphic graphs, I don't need to consider this second one because I've already got it listed above, the 1-edge graph on 3 vertices. So there it is. So that's the key idea, is we don't have labels on our vertex, so we're just looking at structure here. So how about 2 edges? So notice that I have to list or draw them all, so I'm doing it in a systematic way. I'm doing it in terms of number of edges that I'm using. So I've dealt with the 0 edge case, I've dealt with the 1 edge case. Now I want to draw the 2 edge case. What does the 2 edge case look like? Well, there's going to be 1 edge, and then there's really 2 choices left. I could either use this edge here, or I could use this edge here. But either way, I'm getting a path of length 2. They have the same structure. So there we go. I'll just pick one of the edges, use it, and then there's our path of length 2. That's our 2-edge case for 3 vertices. Lastly, if we had 3 edges that we wanted to use, then we'd use all 3 edges. This would give us the complete graph on those 3 vertices. So there's our 3 edges. So there are precisely 4 different shapes of graphs on 3 vertices. There's one that has 0 edge, one that uses 1 edge, a path that uses 2 edges, and a cycle that uses 3 edges. Let's do the same thing with 4 vertices now. So we'll do the same type of enumeration. We'll do all of the ones using 0 edges. There's only one of those. How about the ones that use 1 edge? There would be only one of those, just use an edge. How about the ones that use 2 edges? So there's our 1 edge. So I could make a path, or I could start with this 1 edge and then just use the opposite edge. So those are 2 different ways to have a 2-edge graph on 4 vertices. And then we can do the same thing for 3 edges. Not sure how many we're going to get, but maybe I'll list at least 3 of them down here. Let's see if we can fill them all up. So we're going to have, in all cases, there's going to be one edge. Make that the choice for that one edge. Now I need to add two more edges. So I could add an edge like I've done before. I could, start with this diagram, stick that edge there, and then say where could I put the third edge and so on. Or I'm just going to back up just a moment and say there's no way to add three edges to this diagram and not have a vertex of degree 2. There's going to have to be a vertex of degree at least 2. And so I'll start with that. There's going to have to be a vertex of degree at least 2. So I'll make sure I have that to start with. So there we go. All our graphs on 3 edges are going to have to come from this graph here. So now it's a question of how do I add that third edge in? Well, I can add a third edge in by making a path. I could add a third edge in by making a triangle, or I can add a third edge in by making an arrow. And those are all the 3 possible cases we can have for using 3 edges. Now let's go ahead and do 4 edges. I don't know how many we're going to need, but let's see. So if we're going to do 4 edges, maybe as we start to get bigger, we should take a step back and say all of these graphs were drawn. They're all going to be subgraphs of K4. So they're all going to be subgraphs of this graph here, K4. So if I want to draw a 4-edge graph on 4 vertices, it's really a matter of removing 2 of the edges from K4. And so I can look back here and say, oh, there's really 2 different ways to remove 2 edges. I either remove 2 edges that are disconnected from each other, or I remove 2 edges that form a path. So I should know at this point that there's going to be 2 options over here. And so in the first case, we're going to remove 2 edges that form a path. What I am going to do is the 2 edges that I'm going to remove that form a path are going to be this edge and that edge. And so I get a triangle with an edge attached to it as my graph. And then also I could remove 2 edges that are opposite each other. And so the 2 edges that I've removed are these 2 diagonal edges. And then I get a cycle of length 4. So those are the 2 possibilities I have for 4 edges. What about 5 edges? 5 edges, again, by analogy to the 1 edge case, it's really just you got to remove an edge. If I want 5 edges, I have to remove 1. So what I'll do is I will keep this cycle around, I'll keep a diagonal edge, and I'll remove the other diagonal edge. So there's our 5-edge case. And then we can look at our 6-edge case. Our 6-edge case, that's all of K4. And so there's 6 edges. And so we've listed all the possible graphs we have on 4 vertices here. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible graphs on 4 vertices. And we've counted the graphs by their structure. So there's 11 possible structures we have on 4 vertices. So you're asked in the exercise at the bottom to draw all non-isomorphic graphs with 5 vertices now, but not in general, just focus on the one case where you're using exactly 4 edges. And so I'll leave that to you to ponder. So now we'll focus on the question of how to test if 2 graphs are isomorphic. So there is a spoiler at the bottom. There is no known efficient algorithm for checking graph isomorphisms. So what is it we can do? Well, if we want to show 2 graphs are isomorphic, we have to come up with that function which maps the vertices of one to the vertices of the other and maps their edges accordingly. So that's what we have to do if we want to show 2 graphs are isomorphic. To show they're not isomorphic, we'll just list some properties that are what we call invariant under isomorphism. So that is properties that if 2 graphs are isomorphic, they have to share that property. So we'll list a few properties that such graphs will have. And then what we can do is to show 2 graphs are not isomorphic, we find a property that one of the graphs has that the other one doesn't have. But it should have if they are isomorphic. So if it doesn't have it, then they're not isomorphic. So we'll do an example of that. First, we'll list some properties, and then we'll see an example. So if two graphs are isomorphic, they share the same properties. And so what are some examples of properties that they would share? Well, for one, they would have to have the same number of vertices and the same number of edges. So they would have the same number of vertices. That's because there's a bijection between their vertex sets. And they'd have to have the same number of edges. What else would they have to have in common? Well, they'd have to have the same vertex degrees. So same vertex degrees. If one of them has 3 vertices of degree 2, then the other graph has to have 3 vertices of degree 2, because that's a property of the structure of the graph. What about another property? Well, they'd have to have the same number of cycles of each length. So same number of cycles of each length. You know, if one graph has 4 cycles of length 3, the other graph has to have 4 cycles of length 3. If one graph has 2 4 cycles and a 5 cycle, the other graph has to have 2 4 cycles and a 5 cycle. And so these are kinds of things we can look for in one graph and look for in the other graph, and if we get a difference, then we know the graphs aren't isomorphic. So let's have a look at an example. So we'll look at 2 graphs here, a graph G and a graph H, and our job is to determine whether they are isomorphic or not, whether they have the same structure or not. So far, so good. They have the same number of vertices. So far, so good. They seem to have matching edges. But in G, we get these 2 edges, whereas in H, we have these 2 edges. So now, are these graphs isomorphic? You can pause the video here and come up with a reason for why you think they are isomorphic, and if they are, then come up with a function mapping the vertices of one to the other so that the edges map accordingly. Or if you feel they aren't isomorphic, come up with some property that one of them has that the other one doesn't have. Okay, so I'm assuming you've taken a little bit of time to think about this. Let's start to list some properties. I'm going to go number of vertices. We'll list them in each case. And we've already indicated that they have the same number of vertices. There's 6 in each case, but we'll list them here just to indicate that we have thought about them. What about the number of edges? The number of edges in each case, well, we can count them up. 1, 2, 3, 4, 5, 6, 7, 8 edges in G, and there's also 8 edges in H. So far I'm not finding something that's different to conclude that they're not isomorphic, but I'm still not trying to find this function that shows they're isomorphic. So I'm just trying to get a feel for, do they really have the same structure? What else can I do? I can look at their vertex degrees. And what I'll do is I'll just list the vertex degrees. So I will list them from smallest to largest. So I've got a vertex up at the top that has degree 2, another one down at the bottom that has degree 2, and then the ones around the middle each have degree 3. So there's 4 of them that have degree 3. How about in the other graph H? Well, the top has degree 2, the bottom vertex has degree 2, and the ones around the middle each have degree 3. So they have the same degrees, or what we call the degree sequence. Okay, what's next? Well, I can notice in vertex G that there's a triangle. So there's a 3 cycle. So it has a cycle of length 3. In fact, there's 2 of them. There's a top one and a bottom one, but I'm just going to say, well, at least it has one cycle of length 3. There it is. But if I look at H, there are no cycles of length 3. There are no 3 vertices which make a triangle. So no cycle of length 3. because one of our properties up above, namely this one here, says that if they're isomorphic, they're going to have the same number of cycles of each length, then therefore G and H are not isomorphic. They really do have different structure. So now that we have this notion of what we mean for two graphs to be the same structurally, we can now get into counting problems. In this example, we want to know how many subgraphs of the complete graph on n vertices, so how many subgraphs of Kn, are isomorphic to Kt, the complete graph on t vertices. In this case, t is less than or equal to n. So let's have a look at an example first, just to get a feel for what's going on. Let's just say n is 7 and t is equal to 4. So what we have for 7 vertices is they look like this: 1, 2, 3, 4, 5, 6, and 7. And so the complete graph on 7 vertices would have edges that connect all of these different vertices. So we'd have all of these edges here, and oops, I'm just going to draw a bunch of, we'd have a whole collection of edges. I'm just going to leave those off because what we're interested in is we're interested in trying to find how many copies of Kt are inside Kn. So what would be one example of a copy of K4 inside K7? Well, what I'd have to do is I'd have to just pick 4 vertices. So let's just pick 4 vertices. Maybe I'll pick these 4 here. And then I'd use just the edges that connect these 4 vertices. So there we go. There's a copy of K4 in K7. Are there other copies? Yeah, sure. We can use this vertex 1, we could use the vertex 3. Well, maybe I'll also use 4, and maybe I'll use 7 as well. And so those ones form another copy of K4 inside K7. So there's another copy of K4 in K7. And what we're really interested in is how many different copies are there of K4 inside K7. Well, we've sort of given an indication of how we can possibly count these things through these two examples. All I had to do was select 4 vertices from the 7, and they would induce a subgraph, which is K4. And so that's what I'm going to notice. I'm going to notice that any selection, so we're now out of the example and into the general argument, any selection of t vertices from n, so the n vertices of Kn, induces a subgraph. Remember, induce is a technical term. The induced subgraph is, once you've selected vertices, it's the subgraph which contains all of those edges that are in the original graph that connect those vertices up. So any selection of the t vertices induces a subgraph isomorphic to Kt. And maybe I'll be a little bit more specific. It induces a subgraph of, so I can move it over, but maybe you wrote in pen, so just a little caret, let's insert this, a subgraph of Kn isomorphic to Kt. So really, this is telling me that the number of different subgraphs I have is just the number of ways I can select t vertices from the n vertices of Kn. So therefore, the number of subgraphs is, from those n vertices, how many ways you can choose t of them. And so there we go. We've got how many subgraphs of Kn are isomorphic to Kt, and choose t of them. All right, let's have a look at another example. Let K4, with a little superscript of a minus sign, be obtained from K4 by deleting an edge. So we use this notation to mean K4 with one edge removed. How many subgraphs of Kn are isomorphic to K4 with an edge removed? So let's get a feel for what does K4 with an edge removed look like. So here's K4. And I've removed an edge from it. Which edge have I removed? I removed the edge connecting that vertex to that vertex. So this is K4 with an edge removed. So how many subgraphs of Kn are isomorphic to K4 with an edge removed? Let's get a feel for what's happening here. I've got Kn. I've got lots of vertices in Kn. I'm just going to imagine I've sort of got this big blob, which is Kn here. How am I going to find a copy of K4 with an edge removed in there? What I will do first is I will pick the two red vertices, and maybe I'll color the other ones as yellow. And then I'll pick those two yellow ones in my picture here. So maybe those ones there. So then these determine the subgraph K4 with the edge removed, because what I'm going to do is I'm just going to connect, for the yellow ones, I connect them to everything. And then for the red ones, I just make sure they're connected to all the yellow ones and not each other. And there's our subgraph, K4 with an edge removed. And so that's how we're going to go ahead and count these things. The way we're going to count them is we're going to say first, choose the two vertices you're going to designate as the red vertices. So choose two vertices that will not be adjacent to each other. That's the edge removal part. And then after those are chosen, we've got n minus 2 left, and we're going to choose 2 of those. And that's going to be sufficient to select 4 vertices where there's going to be an edge removal between them. And so this is our number of choices. What is this equal to? Well, this is n factorial over 2 factorial n minus 2 factorial times n minus 2 factorial 2 factorial n minus 4 factorial. And I can see that we get a little bit of cancellation going on here. I get those n minus 2's canceling. And then we also have the n factorial at the top and the n minus 4 factorial on the bottom. That gives me n minus 1, n minus 2, n minus 3, and then n minus 4 factorial cancels with the 1 on the bottom. And then we get the 2 times 2, which is 4. So that's what it boils down to. That's our count for how many K4s with an edge removed are inside Kn. All right, let's have a look at the next example. How many subgraphs of the complete bipartite graph Knm are isomorphic to K34? So K34, what does it look like? It's going to have 3 vertices on one side, 4 on the other, and we've got edges that connect everything on one side with everything on the other side. So that's what our K34 looks like. And we want to find copies of this in Knm. So Knm is going to look like this. There's going to be a bunch of vertices, namely n of them. So that's our vertex set of size n. And then we've got the other half of the bipartition that has m vertices in it. So this is our sketch of Knm. And then we've got edges that go all across from every one of these into the other side. And maybe I'll do that over here as well. We've got all these edges coming out, connecting it to every other vertex. So that's our rough sketch of what a Knm looks like. I'd like to find K34 in there. So how can I do that? Well, one way to do it is to say I've got these 3 yellow vertices and these 4 green ones. Therefore, to count the number of copies of K34 there are in KNM is we first have to say, well, suppose I want to pick from the side with n vertices, I want to pick 3 of those vertices to make yellow. So I'll pick from n 3 of them to be yellow, and then from the other side, that's the m side with m vertices, I'll pick 4 of those to be green. And then each of these selections corresponds to a subgraph of type K34. But what happens if I chose the 4 vertices to live in the other half of the bipartition? So then I have to add to this that I could have made my selection. So from the side with n vertices, I'm going to choose 4 of those to be the green vertices. And then the other side, I will choose 3 of them to be the yellow vertices. And there's my solution. So what we're going to do is we're going to choose the 3 vertex set. And then from the other side, we'll choose the 4 vertex set. And then vice versa. From the side with n vertices, we could choose the 4 vertex set. And then from the other side, we will choose the 3 vertex set. And so there's our solution. All right, let's have a look at the last example. We want to find how many subgraphs of KNN there are that are isomorphic to this graph. Basically a square with an extra edge attached to it. So we're looking at KNN. So the bipartite graph which has equal number of vertices on both halves of the bipartition. So one of the things I'm going to note here is that we're interested in bipartite graphs and how this thing sits inside it. So maybe I should draw it as a bipartite graph. How can I draw it as a bipartite graph? Well, I just color the vertices. So if that's a yellow vertex, it's going to sit in the side with all the yellow vertices. What does it connect to? It connects to a purple one. But then that purple one would connect to a couple of these yellow ones, and then those yellow ones would connect to a purple one. So I see that I could write this as a 1, 3, 5, and then 2, 4. So if I call this 1, 3, 5, 2, 4, then our graph is 1 connects to 2, 2 connects to both 3 and 5, and 4 connects to both 3 and 5. So there is the graph that I'm trying to find inside the bipartite graph. And the nice thing about this one is it tells me that there's going to be 3 vertices that live in one half of the bipartition, 2 vertices that live in the other half. Is this enough if I just say here's 3 vertices and here's 2 other vertices? Is that enough to determine the graph? Well, not really, because if we look closely, this is K3, 2, but there's an edge removed. So we'll call it K32 with an edge removed. So we're going to have to deal with which of those 3 vertices doesn't have the extra edge connecting to it. So the edge that's missing is 1, 4, for example, in that diagram. So how are we going to count the copies of these? Well, what I can do is the following. So I'm thinking of KNN as, I've got n vertices, and then I've got another n vertices, and I've got edges that are going across like this and like this, all possible edges connecting all those n vertices. So that's the visual I have in my mind, is a collection of n vertices on one side and on another, and then all these edges that go across. So how am I going to count these copies? Well, what I have to do is I have to think, I'm going to have to select 3 yellow vertices from one side. So what I'll do is I will first pick from the 2 sides I have for the bipartition, I will pick one of them that's going to be the set where I use 3 of the vertices. So choose side to use 3 vertices. That's like saying I want to choose a side to use 3 vertices. I'll either choose that side or that side. Once I've picked the side, then I've got to go ahead and select my 3 vertices over here, and then I've got to select my 2 over here. Or vice versa, I could use the 3 yellow ones on the right half and 2 green ones on the left half. So that's my selection of side first. Once I've picked a side, then from one of the sides that I've chosen to use 3 from, I'll pick 3 vertices from it. The other side, I will pick 2 vertices from it. And so far, that's given me how many copies of K32 there are in the graph. But now I need to worry about that missing edge. So again, we'll look at our picture. I find it always helpful to draw as the selection process happens. So I've got this selection process. There's n vertices. I've just selected 3 of them. From the other half of the bipartition, I've selected 2 of them. With that selection in mind, I now have all these edges at my disposal, but I want to remove one of them. So what can I do? Well, of those 6 edges, there's 6 edges that connect the yellow and the green vertices. I want to pick one of them and remove it. So of those 6 edges, remove one of them. So let's label what these were. Choose 3 yellow. Choose. So by that I mean choose 3 vertices which you will use as your yellow vertices. Choose 2 purple. And then choose the edge to remove. Because at that point, you've got a K32, but we want K32 with an edge removed. So therefore, pick the edge that you want to remove. Of the 6, choose one and remove it. And so there we are. There's our solution. So we can always look at alternate solutions. I'll give an alternate solution here. How are we going to think about it? The way I'm going to visualize it is, we got 2 halves of the bipartition in K and N. How am I going to build the K32 with the edge removed? Well, the first thing I'm going to do is I'm going to pick 2 vertices from one side and 2 vertices from the other side. So N choose 2, N choose 2. So we're going to choose 2 vertices from each half. And then we get all the edges that connect those vertices. So those are all given to us. Then what do we want to do? Well, then we want to pick one of the sides. So of the 2 sides, we're going to pick one of them. And that's where we're going to choose a 3rd vertex from that side. So choose side for the 3rd vertex. So maybe in our example here, I choose the first side. And then I'm going to pick that 3rd vertex. So once I've chosen the side, of the remaining n minus 2 vertices on that side, we'll pick one of them. And that'll be our 3rd vertex on that side. So choose the 3rd vertex on that side. So now we're at the picture we've got so far. Now what do I want to do? Well, now I want to figure out which of the 2 vertices on the other side I'm going to connect the red one to, because I've got to leave one of the connections off. So of those 2 vertices, I will pick one of them that I'm going to connect to. So of those 2 vertices, pick one of them to connect to. So choose vertex to connect to the 3rd vertex. And once we've done that, that gives us our extra edge. And that also tells us which vertex we aren't connecting to. It's just the one we didn't choose from that side of 2. And so there we are. There's our solution. We've got that this is an alternate way to count the number of such embeddings. And so you can check for yourself. Do these two answers agree? They're both written in slightly different ways. You can expand them out as factorials to see that they actually do give the same result. All right, and I'll leave it to you to maybe come up with different alternate solutions for this. All right, so that's it for this section. Thanks for watching, and we'll see you again next time.